every star a potential sun, yet silence answers. With such staggering numbers, it seems almost inevitable that life, in some form, must exist beyond Earth. This intuition, while compelling, is also the starting point for one of the most profound and unsettling questions in science. If the universe is so vast and full of potential abodes for life, where is everybody? This is the essence of the Fermi Paradox, a cosmic mystery we'll delve into throughout this video. But before we confront the silence, let's first immerse ourselves in the sheer, mind-boggling scale of probability and possibility that underpins this cosmic conundrum. To truly grasp the implications of the Fermi Paradox, we must first confront the astronomical numbers involved. Imagine, for a moment, the Milky Way galaxy alone. Our home galaxy is a majestic spiral, approximately 100,000 light-years across, containing an estimated 100 to 400 billion stars. Now, consider that recent exoplanet discoveries, particularly from missions like NASA's Kepler Space Telescope, suggest that planets are not just common, but ubiquitous. The data indicates that, on average, every star in our galaxy likely hosts at least one planet. This means there could be hundreds of billions of planets within the Milky Way alone. But the numbers don't stop there. A significant fraction of these planets are thought to reside within the habitable zone of their respective stars, the region where conditions are just right for liquid water to exist on the surface, a key ingredient for life as we know it. Conservative estimates suggest that tens of billions of Earth-sized planets might exist within the habitable zones of Sun-like stars in our galaxy. For instance, a 2013 study based on Kepler data estimated that 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. That translates to roughly 8.8 billion potentially habitable Earth-sized planets in the Milky Way galaxy. More recent analyses, incorporating data from the Gaia mission, have further refined these estimates, with some suggesting even higher numbers. For example, a 2020 study estimated that there could be as many as 6 billion Earth-like planets in the Milky Way, and our galaxy is just one among billions. Current estimates suggest there are at least 2 trillion galaxies in the observable universe. If each of these galaxies contains hundreds of billions of stars, and each star, on average, has at least one planet, the total number of planets in the observable universe truly defies comprehension. We are talking about septillions of planets, a 1 followed by 24 zeros. Even if only a tiny fraction of these planets are suitable for life, the sheer volume suggests that the universe should be teeming with it. Let's break down the probabilities further, considering the various steps required for life to emerge and evolve. First, there's the formation of a star system with stable planetary orbits. We know this is common. Next, the presence of heavy elements, the building blocks of planets and life, which are forged in the hearts of stars and dispersed through supernovae. The universe has had billions of years for these processes to occur, with early generations of stars enriching the cosmic medium. Our own solar system formed relatively late in the universe's history, suggesting that many other systems had a head start. Then comes the origin of life itself, a process known as abiogenesis. While the exact mechanisms are still a subject of intense scientific research, experiments like the Miller-Urey experiment demonstrated that organic molecules, the precursors to life, can form spontaneously under conditions thought to exist on early Earth. Furthermore, the discovery of extremophiles on Earth, organisms thriving in environments once thought to be inhospitable, such as hydrothermal vents, deep underground, or in highly acidic or radioactive conditions, expands our understanding of where life could potentially take hold. This suggests that life might be incredibly resilient and adaptable, able to emerge and persist in a wider range of planetary conditions than previously imagined. The existence of life around hydrothermal vents, for example, demonstrates a pathway for life to arise and thrive without direct sunlight, relying instead on chemosynthesis. Consider also the time frame involved. The universe is approximately 13.8 billion years old. Our solar system formed about 4.6 billion years ago, and life on Earth emerged relatively quickly, within the first billion years. Complex multicellular life took much longer, appearing around 600 million years ago, with intelligent life a very recent phenomenon. This timeline implies that if life can arise relatively quickly given the right conditions, then countless other planets could have hosted life for billions of years longer than Earth has. This extended time frame provides ample opportunity for life to not only emerge, but to evolve, diversify, and potentially develop intelligence and advanced civilizations. The concept of a Goldilocks zone for life extends beyond just liquid water. It also encompasses factors like a stable star, a planetary magnetic field to protect against stellar radiation, and the presence of a large moon to stabilize the planet's axial tilt, leading to more stable climates. While these factors might reduce the number of truly habitable planets, the sheer scale of the universe means that even with stricter criteria, the numbers remain astronomically large. For instance, the presence of Jupiter in our solar system is thought to have played a crucial role in deflecting comets and asteroids, thus reducing the frequency of devastating impacts on Earth. Could such planetary protectors be common, or are they a rare cosmic lottery win? Even if the probability of life arising on any given planet is exceedingly small, when multiplied by the septillions of planets in the observable universe, the expectation value for the number of planets harboring life becomes enormous. It's like flipping a coin a quadrillion times. Even if the coin is heavily weighted, you'd still expect to see a significant number of heads. The universe, in this analogy, is flipping an unimaginable number of coins, each representing a chance for life. Furthermore, the concept of life as we know it might be too restrictive. Our definition is based on carbon-based chemistry and liquid water, but could there be other forms of life based on different chemistries or solvents? Silicon, for example, shares some chemical properties with carbon and could theoretically form complex molecules. While speculative, the possibility of exotic life forms further expands the potential. So, when we look up at the night sky, we are not just seeing stars. We are seeing billions upon billions of potential homes for life. The statistical argument for the widespread existence of extraterrestrial life, even intelligent life, seems overwhelmingly strong. This profound sense of probability, of cosmic abundance, is what makes the Great Silence so utterly perplexing. It sets the stage for the Fermi Paradox, a question that challenges our assumptions and forces us to confront the possibility that our understanding of life, the universe, or both, might be fundamentally incomplete. The cosmic ocean, with its boundless possibilities, should be teeming with voices, yet all we hear is silence. And it is this silence that we must now try to understand. This brings us to one of the most profound and unsettling questions in science: the Great Silence. It's the core of what we call the Fermi Paradox, named after the brilliant physicist Enrico Fermi. In 1950, during a casual lunchtime conversation at Los Alamos, Fermi famously blurted out, "But where is everybody?" This seemingly simple question encapsulates a profound contradiction. Given the vastness of the universe, the billions of stars, and the high probability that many of them host habitable planets, why haven't we found any evidence of extraterrestrial civilizations? Let's break down the reasoning behind this paradox. Our own Milky Way galaxy alone is estimated to contain between 100 billion and 400 billion stars. Current models suggest there could be billions of habitable worlds within our galaxy. If even a small fraction of these planets developed life, and an even smaller fraction of those developed intelligent, technological civilizations, the galaxy should be teeming with them. Furthermore, given the age of the galaxy, roughly 13.8 billion years, and the relatively short time it would take for a technologically advanced civilization to colonize the entire Milky Way, tens of millions of years, a blink of an eye in cosmic terms, we should expect to see widespread evidence of their presence. Yet, we observe nothing. This stark absence of evidence, despite the high probability, is the essence of the Fermi Paradox. To quantify this probability, scientists often refer to the Drake equation, formulated by astronomer Frank Drake in 1961. This equation attempts to estimate the number of communicative civilizations in our galaxy by multiplying several factors: the rate of star formation, the fraction of stars with planets, the number of planets per star that could support life, the fraction of those planets where life actually develops, the fraction of those where intelligent life emerges, the fraction of intelligent civilizations that develop detectable communication technology, and finally, the average lifespan of such civilizations. While many of these parameters are still highly speculative, even conservative estimates often lead to a significant number of potential civilizations in the Milky Way. For instance, using some of Drake's original ballpark values, the equation could suggest around 10 civilizations in our galaxy capable of communication. Other estimates, using larger values for the parameters, can yield results as high as 15.6 million civilizations. The paradox then becomes even sharper. If these numbers are even remotely accurate, where are all these voices in the cosmic ocean? The search for extraterrestrial intelligence, known as SETI, has been actively listening for decades. Modern SETI efforts began in the late 1950s and early 1960s with pioneers like Frank Drake and Project Ozma, which used radio telescopes to listen for signals from nearby stars. Later initiatives, such as the NASA Microwave Observing Program and the Breakthrough Listen Project, have continued these efforts, scanning vast swathes of the sky for electromagnetic signals that might indicate intelligent life. Despite these dedicated searches, including the detection of the famous WOW signal in 1977, which remains unexplained, no confirmed evidence of extraterrestrial intelligence has ever been found. This persistent silence in the face of our persistent listening only deepens the mystery. The lack of observable alien civilizations isn't just about not hearing radio signals. It also extends to a lack of physical evidence. If advanced civilizations are indeed common and capable of interstellar travel, we might expect to see megastructures like Dyson spheres, hypothetical constructs built around stars to harness their entire energy output. These colossal engineering projects would be detectable through their infrared signatures as they radiate waste heat. The Kardashev scale, a classification system for hypothetical civilizations based on their energy consumption, describes a Type 2 civilization as one capable of harnessing the total energy output of its star, often through such megastructures. A Type 3 civilization would control the energy of an entire galaxy. If such civilizations existed, their presence would be profoundly evident. Yet our telescopes reveal no such galactic-scale engineering. The Fermi Paradox, therefore, isn't just about a philosophical pondering. It's a scientific problem rooted in our understanding of probability, the age of the universe, and the capabilities we project onto advanced life. It forces us to question our assumptions about how life evolves, how intelligence develops, and how civilizations behave once they reach a certain level of technological prowess. The cosmic ocean, with its boundless possibilities, should be teeming with voices, yet all we hear is silence. And it is this silence that we must now try to understand. The cosmic ocean, with its boundless possibilities, should be teeming with voices, yet all we hear is silence. And it is this silence that we must now try to understand. The silence is, of course, the heart of the Fermi Paradox. Proposed by physicist Enrico Fermi in 1950, it highlights the stark contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. With billions of stars in our galaxy alone, many with planets and habitable zones, it seems statistically improbable that Earth would be the sole cradle of intelligent, technological life. Yet, here we are, listening to static. So what are the potential solutions to this profound cosmic mystery? One category of solutions suggests that intelligent life is simply much rarer than we initially estimated. This brings us to the rare Earth hypothesis. This idea posits that the emergence of complex, multicellular life, and especially intelligent life, requires an incredibly improbable convergence of astrophysical and geological events and conditions. It's not just about a planet being in the habitable zone of its star. It's about having the right kind of star, a stable planetary system with gas giants like Jupiter to clear away dangerous asteroids, a planet of the right size with a molten core for a protective magnetic field and plate tectonics, and even a large moon to stabilize its axial tilt. Each of these factors, and many more, are considered crucial for the long-term stability and evolutionary pathways necessary for complex life to arise. If any one of these conditions is slightly off, the chances of complex life, let alone intelligent life, plummet dramatically, making Earth not just rare, but perhaps exceedingly, fantastically rare. Another set of solutions doesn't deny the abundance of life, but rather proposes reasons why we haven't detected it. Perhaps civilizations are out there, but they simply don't last long enough to become detectable across interstellar distances. This is the self-destruction hypothesis. It suggests that technological civilizations, upon reaching a certain level of advancement, inevitably develop the means to destroy themselves, whether through nuclear warfare, environmental catastrophe, uncontrolled artificial intelligence, or other self-inflicted disasters. The argument is that the capacity for self-destruction grows faster than the wisdom and political structures to control it. If this is a common trajectory for intelligent species, then the window for detection would be incredibly brief, explaining the cosmic silence. A more unsettling possibility is offered by the dark forest theory, a chilling concept popularized in science fiction. This hypothesis suggests that the universe is a dangerous place, a dark forest, where every civilization is a silent, armed hunter. The reasoning is that because the intentions of any newly encountered civilization can never be known with certainty, the safest course of action is to eliminate any potential threat before it can eliminate you. In this scenario, broadcasting one's presence is an act of extreme peril, leading all advanced civilizations to remain hidden and silent, lest they attract unwanted, destructive attention. The silence, then, isn't an absence of life, but a testament to its fear. Then there's the zoo hypothesis, a less grim but equally profound explanation. This idea proposes that extraterrestrial civilizations are aware of our existence, but intentionally avoid contact, much like we observe animals in a zoo. The motivation could be a prime directive of non-interference, allowing nascent civilizations like ours to evolve naturally, without contamination or undue influence from more advanced species. They might be waiting for humanity to reach a certain level of technological or social maturity before revealing themselves, or perhaps they have simply designated Earth as a protected reservation. In this view, the silence is a deliberate choice, a cosmic quarantine. Another intriguing solution is the transcension hypothesis. This theory suggests that sufficiently advanced civilizations don't expand outward into the physical universe, but rather turn inward into inner space. They might migrate into computationally optimal domains, perhaps even black holes, where they can achieve vastly greater efficiency and complexity in their existence. In this scenario, physical expansion into the galaxy becomes an outdated and inefficient pursuit. If civilizations transcend to these highly miniaturized and efficient scales of space, time, energy, and matter, they would effectively disappear from our observable universe, becoming undetectable to our current methods. Related to this is the simulation hypothesis, which posits that our entire reality, including the universe we perceive, is an artificial computer simulation. In this context, the absence of extraterrestrial life could be a design choice by the simulators. They might have simply chosen not to render other intelligent civilizations, or perhaps they only render what is necessary for our simulated experience, saving computational resources. The silence, in this case, would be a feature, not a bug, of our simulated reality. Finally, there's the possibility that we are simply too early. The universe is vast and ancient, but perhaps the conditions for intelligent life have only recently become widespread. If life takes a long time to evolve to a technological stage, we might be among the first. Or perhaps, even if many civilizations exist, they are too far apart in space and time for their signals to reach us, or for us to detect them with our current technology. The sheer distances involved mean that any signal would take thousands, even millions of years to traverse the galaxy, making synchronous communication virtually impossible. Even self-replicating probes, like the theoretical Bracewell von Neumann probes, which could explore the galaxy in a few million years, haven't been detected. This suggests either that such probes are not being sent, or they are designed to be undetectable, or perhaps they simply haven't reached us yet. This brings us to one of the most compelling and unsettling proposed solutions to the Fermi Paradox, the Great Filter. The Great Filter hypothesis suggests that somewhere along the evolutionary path from the emergence of life to a highly advanced, interstellar colonizing civilization, there exists at least one extremely improbable or difficult step, a filter that few, if any, civilizations ever pass through. This barrier could be a singular event or a series of highly unlikely occurrences that prevent life from progressing to a detectable, technologically advanced stage. The core idea is that the vast number of potential sites for intelligent life in the universe is drastically reduced to the tiny number we actually observe, currently just one, humanity, by this filter. The Great Filter can be thought of as a cosmic bottleneck. If it lies in our past, it means we are incredibly rare. However, the more unsettling possibility is that the Great Filter lies ahead of us. This means that many civilizations might reach a similar technological stage to our own, or even surpass it, only to be wiped out by some catastrophic event or inherent flaw before they can expand into the galaxy. This future filter could manifest in various ways, often linked to the very advancements that define an intelligent civilization. One prominent candidate for a future Great Filter is self-destruction. As civilizations become more technologically advanced, they also develop the means to annihilate themselves. Nuclear warfare is a frequently cited example. Humanity has lived under the shadow of global thermonuclear war for decades, and while mutually assured destruction has thus far prevented such a catastrophe, it remains a theoretical possibility for any advanced civilization. Similarly, unchecked climate change, driven by industrial activity, could render a planet uninhabitable for its creators. Another terrifying prospect for a future filter involves artificial intelligence. The creation of advanced AI, particularly artificial general intelligence, AGI, is often seen as a pivotal moment for a civilization. While AI promises solutions to many of humanity's biggest problems, from disease to climate change and even space travel, it also presents profound risks. An AI could become misaligned with its creator's goals, leading to unforeseen and potentially catastrophic outcomes. It could also lead to a slow erosion of human capacity and resilience if societies become overly reliant on AI systems, making them vulnerable if those systems fail or are turned against them. The paradox here is clear. The very intelligence we create to propel us forward could be the ultimate barrier to our survival. Some even speculate about a berserker hypothesis, where a filter exists between advanced civilizations and galactic colonization, with each emerging civilization being destroyed by a lethal von Neumann probe created by a more advanced and perhaps hostile civilization. Other potential future filters could be natural, external events that no civilization, regardless of its technological prowess, can prevent. These might include devastating asteroid impacts, nearby gamma-ray bursts, or intrusive supernovae that could sterilize entire planetary systems. While we are developing technologies to mitigate some of these risks, such as asteroid deflection, our current capabilities are limited, and some cosmic events are simply beyond our control. The implications of the Great Filter are profound. If the filter is in our past, it suggests that we are incredibly unique, perhaps even alone, in the observable universe. This would make humanity a truly special occurrence, having navigated a treacherous evolutionary path that few, if any, others have. This perspective, while perhaps appealing to our sense of significance, also places a heavy burden of responsibility on us as the sole known intelligent life. Conversely, if the Great Filter lies in our future, then the silence of the cosmos is not a sign of our uniqueness, but a chilling premonition. It means that civilizations tend to reach a certain point of development, perhaps similar to our own, before encountering an insurmountable obstacle that leads to their demise or prevents their expansion. In this scenario, every radio signal we send out, every probe we launch, might simply be delaying the inevitable encounter with our own filter. The longer we fail to detect other civilizations, the more likely it becomes that the filter is still ahead and that our future is precarious. The Great Filter forces us to confront the fragility of intelligent life and the potential for self-destruction or the overwhelming power of cosmic forces. It transforms the question of "where are they?" into a more urgent and introspective "what will stop us?" The absence of self-replicating probes, like the theoretical Bracewell von Neumann probes, which could explore the galaxy in a few million years, hasn't been detected. This suggests either that such probes are not being sent, or they are designed to be undetectable, or perhaps they simply haven't reached us yet. The Great Filter offers a stark alternative. Perhaps no civilization has yet survived long enough to deploy them on a galactic scale, or those that did met their end shortly after. The Fermi Paradox, the perplexing silence in a seemingly life-filled cosmos, forces us to confront profound questions about our own existence and future. It's a cosmic mirror reflecting our hopes and fears, challenging our assumptions about life, intelligence, and civilization. The implications for humanity are vast, depending on where the Great Filter, that hypothetical barrier preventing civilizations from reaching interstellar maturity, ultimately lies. If the Great Filter is firmly in our past, meaning that the emergence of life, or perhaps complex multicellularity, or even the development of intelligent tool-using species like us, was an incredibly rare fluke, then we might be among the first, if not the first, intelligent civilization in our galaxy, or even the observable universe. This scenario, while perhaps a blow to our desire for cosmic companionship, would imbue humanity with an almost incalculable significance. We would be the exception, a testament to an improbable chain of events, making Earth a truly unique and precious sanctuary of life. This perspective suggests a profound responsibility to cherish and protect our singular planet and the life it harbors, for we might be the only conscious observers in a vast, otherwise empty, cosmic expanse. The Great Silence would then be the natural state of the universe, not a graveyard, but a pristine wilderness waiting to be explored by its first intelligent inhabitants. However, the more unsettling possibility is that the Great Filter lies ahead of us. This suggests that civilizations, once they reach a certain level of technological advancement, inevitably encounter a barrier that prevents their long-term survival or expansion. This future filter could manifest in numerous ways, many of which are already concerns for our own civilization. One of the most frequently cited potential future filters is self-destruction, particularly through advanced weaponry. Nuclear warfare, for instance, has long been a specter haunting humanity, while mutually assured destruction has, to date, prevented global thermonuclear war. The existence of such destructive power highlights a precarious stage in any civilization's development. The ability to annihilate ourselves is a relatively recent acquisition in our 200,000-year history, and it's a capability that could easily be a common pitfall for emerging technological species. Another looming threat is environmental catastrophe, such as runaway climate change. Our current trajectory with global warming demonstrates humanity's capacity to profoundly alter our planet's life support systems, potentially to our own detriment. If civilizations consistently fail to manage their impact on their home worlds, then environmental collapse could be a recurring great filter. Perhaps the most discussed and rapidly evolving potential future filter is artificial intelligence. As AI continues to advance, the question of aligning its goals with human well-being becomes paramount. A non-aligned superintelligence, or even an over-reliance on AI that erodes human capacity for autonomous action and adaptation, could lead to a systemic collapse or an existential risk for our civilization. Some theories suggest that once a civilization reaches the threshold of autonomous AI cosmoindustry, their expansion might shift to a quiet mode, driven by rational goals like survival, diversification, and knowledge preservation, rather than loud, resource-hungry empires. This could explain the silence, as advanced AI civilizations may simply not be detectable by our current methods. The development of artificial life itself, as a great filter, could lead to systemic collapse or existential risk for the originating civilization. Other speculative future filters include engineered pandemics, where biological threats, either accidental or intentional, could decimate a population. Or perhaps we could encounter a cosmic booby trap scenario, where the very act of interstellar expansion or the search for extraterrestrial intelligence inadvertently triggers a catastrophic event or unleashes a dangerous technology left by a previous, fallen civilization. This suggests that exploration itself could be a vector of annihilation. The concept of the Great Filter also forces us to consider the dark forest hypothesis, which posits that the universe is a dangerous place where intelligent civilizations remain silent to avoid detection by potentially hostile others. In this scenario, broadcasting our presence, as humanity has done with messages like the Arecibo message, could be an act of profound naivete. The silence, then, would not be an absence of life, but a testament to the wisdom of those who choose to hide. The implications of the Fermi Paradox and the Great Filter are not merely academic. They profoundly influence our understanding of humanity's place in the universe and our trajectory. If the filter is behind us, we are incredibly fortunate, and our efforts should focus on preserving our unique existence and perhaps, eventually, becoming the galactic civilization we've so far failed to detect. This perspective might even suggest that our current search for extraterrestrial intelligence, SETI, is a search for our own past, for the rare steps that allowed us to emerge. However, if the filter lies ahead, then the Fermi Paradox serves as a stark warning. It compels us to address the existential risks we face with renewed urgency. It highlights that our technological progress, while impressive, may be outpacing our wisdom and our ability to manage the consequences of our own creations. Climate change, nuclear proliferation, and the uncontrolled development of advanced AI are not just earthly problems. They could be universal challenges that every technological civilization must overcome to survive. The very act of pondering the Fermi Paradox and the Great Filter encourages introspection. It forces us to consider what truly defines an advanced civilization. Is it merely technological prowess, Or does it encompass a sustainable relationship with its environment, a peaceful coexistence among its members, and a wise stewardship of its own future? The Great Silence could be a profound lesson, a cosmic cautionary tale whispered across billions of years. Ultimately, the answer to the Fermi Paradox will profoundly shape our understanding of our place in the universe. Whether we find aliens or confirm our solitude, the journey to resolve this cosmic mystery will redefine our identity. It underscores the critical importance of continued scientific inquiry, particularly in areas like exoplanet research, astrobiology, and SETI, which are actively analyzing exoplanet atmospheres and scanning for signals. The search for extraterrestrial intelligence is not just about finding others. It is also about understanding ourselves. It's a call to action, urging us to overcome our challenges and strive for a future where humanity not only survives but thrives, perhaps eventually joining a galactic chorus we currently cannot hear, or perhaps becoming the first voice in a silent universe.